this flipped lecture is on 6.5, which is on drag. I put drag in quotes. The reason I put drag in quotes is because in English, we use drag and friction pretty interchangeably. So we'll say someone is dragging their feet. But Knight uses drag a little bit differently than the English usage of drag. When he's talking about drag, he's specifically talking about wind resistance. Okay, so here's a person that's falling, and because it's kind of hard to draw wind resistance, I've made all these little like lines here that look like, okay, this person's falling, and this is supposed to represent the disturbed air behind them. Now the free body diagram for this situation is actually very similar to the free body diagram for this situation. This was a person standing on a scale in an elevator. Let's look at the free body diagram for the person. We could say the length of that vector n is n, and now we know from section 6.3 that that length of that vector f sub g is m little g. So if you were to write down the equations, it's always F net is equal to MA. In this case, there's two forces, so that's Fg plus N is equal to MA. But those forces only go in the y direction. And what's the y component here of this equation? Well, we've got Fg in the downward direction, so that's minus Mg. We've got n in the upward direction, and its length is n, so that's plus n. And then on the right-hand side, the y component of ma is ma sub y. Now this is actually an extraordinarily similar situation. And so if we want to go and analyze this, it's the identical kind of work. Let me show you how crazily similar this is, okay? You always have F net equals MA for every object in your diagram. So that, of course, is unchanged. Here we had the two forces as being Fg and N. Over here we have the two forces as being Fg and F drag. So the only thing that changes there is that this is F drag. If we want to take the y component of this vector equation, we still have that the length of the gravitational force vector is mg, and it points in the minus y direction. And instead of having a normal force pointing up in the up direction, we now have a drag force in the up direction. Okay, so in this case, where the person is falling downwards, the drag force is in the upward direction, and we're going to model that as some constant E times the speed squared. This is your first example of a force that's velocity dependent. So the length of this vector is ev squared, and the direction is opposite the velocity. If this person were going through the air, say on a bicycle this way, then the drag force would be that way. The next thing I'm going to do with this equation is I'm going to solve it for a sub y. Now we can have two situations here, or actually really three situations. The third one doesn't occur very often. One situation is that mg is bigger than ev squared. So three situations. One situation is mg is greater than ev squared. In that case, if mg is a larger number than ev squared, then minus mg plus ev squared is a negative number, which means you have acceleration in the downward direction. Second case, mg equals ev squared. This is what we call terminal velocity. When v gets so large that ev squared is now equal to mg, then these two forces balance. And the way you see that here is if ev squared is equal to mg, then minus mg plus ev squared adds up to 0. So once they balance, you're no longer accelerating. Now we can have an expression for terminal velocity. We can even solve it. It's the square root of mg over e. Now there's actually a third case. The third case would be if you're falling faster than terminal velocity. Maybe somebody shot you out of the bottom side of a hot air balloon with a cannon. And so for a while, you're going faster than terminal velocity. In other words, for a while, EV squared is greater than mg. If EV squared is greater than mg, that means that you'll have a positive a sub y, which means if you're going down, you're going to be slowing. So that's the third case. It doesn't happen as often as the first two cases. Now I want to say one last thing before I close out this video. I wrote that the magnitude of the drag force was EV squared. Now if you look at Knight 6.15, he says the magnitude of the drag force is 1/2 C rho A V squared. Okay, now that makes this situation that I just analyzed look a heck of a lot more complicated than it actually is. The only difference between what Knight wrote and what I wrote is I called this entire mess right here, I called that E. Now, you know, Knight doesn't do things just to make things extra complicated, okay? And the reason he did it this way is that if you do it this way, then C is a pure number and is called the coefficient of drag. And so if you've heard that, you know, somebody has a really slippery car that's very aerodynamically shaped, you might find that it has a, say, a coefficient C, which is less than 0.3. And if you have someone that may be a very boxy car, maybe the coefficient of drag might be like 0.45. We can check that if C is a pure number, that this whole rest of this expression has the units of newtons in the MKS system. So what are these other things? I haven't even defined them yet. Let's define them. Rho is the density of the medium you're going through. So that's the mass per unit volume. So if you have a volume of air, and that volume of air has some mass, which I'll call capital M, and the volume, which is length times width times depth, the volume V, which is equal to LWD, is V, then mass over volume of the air is called the rho, or the density of the air. So that's what that is, and in the MKS system, that has units kilograms per meter cubed. This term here represents the cross-sectional area of the thing that is going through the air. So if you're looking at, say, the front of a car, and here's the passenger area, and here's the front of the car, and here's the wheels, you would take all of that area right there, all of the area that you can see looking at the car head on, and you would call that the cross-sectional area of the car, looking at it head on in the direction that it moves through the air. And of course that has dimensions, an area has dimensions meters squared. Meanwhile, V squared has dimensions in the MKS system, meters per second, and that's squared. Let's count that all up. We've got 1, 2, 3, 4 m's in the numerator and 1, 2, 3 m's in the denominator. So that means that we have meters in the numerator. We have seconds squared in the denominator, and we have kilograms in the numerator. And so if you write things in terms of a pure number times the density of the medium times the cross-sectional area of the object times the speed of the object squared, then indeed that thing has dimensions of newtons.